Barton. Okay, let's start today's seminar. Today's speaker is Mariam Khaldieh from
LMU Munich.
Here talk about the mimetic inflation and self-reproduction. Please start when you're ready.
Thank you for inviting me to talk. It's a pleasure to be here at KIOS. It's my first time in Korea, and it's a pleasure to have met some of you and talk to you. And today I will present to you my recent work with Slava and our other collaborator, Ali Shamsuddin. And I will be presenting a theory of, which encompasses many models of inflation that particularly target the problem of self-reproduction. And self-reproduction is a problem that accompanies the theory of inflation in most of the models that are presented in the literature. So we will be addressing this today, in addition to other challenges that face the theory of inflation. In fact, the inflationary paradigm was put in trouble when Paul Steinhardt and Anna Ies published this work after Planck released the results from their observations. And so here they tackle two problems. One is related to the multiverse and therefore the unpredictability of the inflation as theory. And they talk a bit about the initial conditions problem. Now, I will focus mostly in this talk about the multiverse and therefore the unpredictability of inflation. But this paper got a lot of noise and a lot of people argued against many of these points, but the problems are still here today with the models of inflation, and we need to address them regardless of different opinions, different directions. Some people even started taking different directions as to explain the homogeneity, flatness of the universe in a framework that is outside inflation. But we will stick to inflation and we will try to defend these the points and present a framework that actually solves these problems. Actually, there are other criticisms that target inflation, and one problem is also the how likely it is to start inflation in any model. This particular problem I will actually not talk about a lot because the measure that is used to defend this likeliness that is usually defined on the phase space, it's not very well defined. Therefore, I will not comment so much about it, but other works have discussed this issue. And currently, it is just not decided yet whether this measure is really appropriate to make any concrete conclusions from it. So I will just simply ignore this problem for now. Also, another problem or criticism that is addressed in inflationary paradigm is model simplicity, which is how simple should our inflation model be, and maybe how far can we go as in to explain more things with a more complicated model, or appeal to the naturalness of inflation, as in inflation can happen in a framework of any simple model that can address each problem at a time. Obviously, that's not a very good approach, and hopefully today I will show you that with one model we can address many actually problems. Another problem is the fine-tuning of initial conditions. It's going to be slightly tied to this multiverse problem, and I will talk about it a bit in more detail when I explain the self-reproduction problem, and which hence leads to the multiverse. And I will talk briefly about the trans-Planckian problems of perturbation in the context when I describe or when I get to the cosmological perturbations part of our paper. There are, of course, other criticisms, but I will mainly address these 3 points and hint tangentially on this point. So just to give a brief introduction to the slow roll regime of inflation, because Planck results favored models that have a plateau in their potential versus other more simple models that could just be power law inflations. So I think it's useful to just very briefly sketch the rough picture so that if anyone is not very familiar. So we have a scalar field and the potential in the action, which drives inflation. the potential is some variation of this kind of potential with a plateau. And the scalar field equation of motion is described with this equation. And then the scalar factor evolution is described by the Friedmann equation. And here the kinetic energy and the potential both enter into play. Specifically in the plateau models, we enter what is inflation, or better said, inflation is started and proceeds in a slow roll regime, in which actually when the field rolls down from the potential slightly and reaches this plateau, the second derivative is actually is then compared to the other terms in the equation of motion very, very small, so we can ignore the second derivative, and hence the equation of motion is reduced to this very simple equation. And also the potential contributes more to the evolution of the scale factor, so the kinetic energy is also negligible compared to the potential contribution, which is also a particularity for the plateau models. But as we will see that in our model, for instance, it's not going to be the case. However, we will have the case that the second time derivative is going to be ignored, but not the same energy contribution from the scalar field will be driving the inflation at some instances. So these are the slow roll conditions summarized. And this will be important, this condition specifically, when I talk a bit later about the self-reproduction conditions. And one last point here, it's worth noting that the field is decreasing according to this expression here, which we got from the simplification of the equation of motion. And this will be important because we want to track later the decrease in the field as inflation progresses, and we will see how that overlaps with the quantum perturbations. Okay, so now with that in mind, I will formulate the problem of self-reproduction and hence the multiverse problem, and also hence the predictability problem in inflation. So consider a patch of a causally connected region of size inverse the Hubble scale. In this patch, we have the scalar field, and we have also just perturbations imposed on this patch. So if we consider a small brief amount of time, which is proportional to inverse Hubble. So what happens is that this patch expands, and then it produces equal causal regions like this patch around the order of actually 20 patches during this time. So we have then 20 of these causally connected regions within this time. And then during this time, the classical field is decreasing, and it is decreasing according to the previous equation that we saw regarding the slow roll. So we just have the velocity multiplied by this duration of time. And then we see that the field is decreasing generically as phi dot over h. Now, during this time also, the relevant perturbations that we want to account for are going to be the perturbations which have a wavelength that is comparable to the size of this causal patch, right? And this is going to be one inverse of h. So the amplitude of these perturbations is going to be around the order of h. So now, when we follow...
Quantum. You want to say quantum, aren't you? Quantum.
Yes, quantum. I put the index here. So now the total contribution of the change in this classical field and the change in the contribution of the quantum perturbations imposed on this classical field are going to give us this expression. And here is the key moment to understand self-reproduction. So if the total change in the field is positive, it means our field is increasing, which means if we go slightly back to the potential picture, the field will be sliding down, but its average value over this patch will be kicked up slightly by these quantum perturbations that add to the value, and hence the field is kind of staying in this plateau region, which is driving inflation, and hence it is in fact not leaving inflation during this amount of time. And if it's And if this process keeps on going, it means the field never leaves the plateau, and we have what we call an eternal inflation. But if we want this total, and we do want this total field to decrease, then we can impose a condition to avoid this self-reproduction, which is the eternal reproduction of these volumes by exponential expansion. Then we want this negative term to override the h, and then we can avoid self-reproduction. Now, this is a key moment. In the plateau models that, in fact, Planck data favors, we have that the decline of the classical field is described by this, and because we impose the slow roll conditions on the field from the previous equation from the previous slide, I just substitute here the values for h, which was proportional to the potential, and phi dot is decreasing like the derivative of the potential. And this was exactly the slow roll condition that we had. So if in the plateau model, in the background picture, we want inflation, we want to have this condition satisfied. So this term will be strictly much less than 1. So now we are faced with two options, really. One of the options is that if we don't really want to fine-tune the initial conditions of inflation, that is, if we don't want to start with many of these causally disconnected patches and then drive inflation, therefore we need to have a huge degree of fine-tuning depending on how many of these patches are there. Or we can say that we don't want any degree of fine-tuning, or at least a lesser degree of fine-tuning, and then we would like to start with a smaller patch of this region. And therefore, if we want to drive inflation with less fine-tuning, then we would like to start inflation with a small patch. But then h here will be of order of 1. This factor will be very, very much less than 1. And then self-reproduction condition is satisfied, and we have eternal inflation if we don't want to fine-tune. But then if we do want to fine-tune, then, or if we don't want to have self-reproduction, we are then left with a problem of fine-tuning. And in most, or in all plateau models that are known, these problems are there. So we are, if you don't want self-reproductions and the implications that I will talk about in a bit, then you are stuck again with a high level of fine-tuning of initial conditions.
Sorry.
Yes.
Please.
Okay. I ask a question.
Yes, of course.
For this,
Yeah.
the red line is not the Hubble inverse, it's just Hubble, not -1.
Yes.
It should be no minus.
Yeah. Oh,
Right.
here, yeah.
Okay.
Yes, sorry. This is a typo.
And another question is,
Yeah.
the classical field actually is, the mean field is homogeneous.
Yes.
Yeah, the k equals 0. The wavelength is infinite.
Sorry?
The wavelength is infinite.
Yeah, but this is the
Homogeneous.
classical field.
Yeah, classical.
Yes.
But you're talking about quantum fluctuation is within this Hubble volume. So I just don't know how to compare.
It's
with
just that
two quantities in different wavelength, in different.
it's just that if I take a look at this picture here, I can imagine that there's a homogeneous background of my classical field, and then these are just quantum fluctuations that exist in this patch. I can immediately see that the quantum fluctuation that will be relevant for me to be superimposed is the one that's going to have its wavelength really proportional to the size of this causal domain, right? And only then its amplitude will be relevant for us to add, which is why I only considered quantum fluctuations that have the wavelength of this specific causal patch, because others will not have a very significant contribution anyway. So I only imposed this type of quantum fluctuations on the background field, and this is the only contribution that adds to it. But as we can see, apparently this contribution is could be quite significant, and it could prevent the field from sliding down and inflation from ever ending.
Maybe silly question. Why the quantum fluctuation have only kickback side? I mean, the quantum fluctuation can also affect to going down to the other side can affect to the other side.
You mean on the patches that are around it?
I mean, maybe in previous slide.
Oops.
Why the quantum fluctuation affect to kick back?
Yeah, this is a good point actually. So when I first talked about this duration of time, I said that this Hubble patch it's gonna expand. So we're gonna create many more of these Hubble patches around, right?
Okay.
So then in this patch here, this wavelength might add positively to the average value of the field. It might add negatively to the patch that's right next to it. But this is exactly the point, which I will then move to my other slide to continue the point, is that it is enough for me that I have in one of these causal domains that the field is continuously kicked back and not below, and then this small ball will then start inflating in its own margins, because here the field is going to continue inflating, the region is going to continue inflating. Here, outside of that, where maybe the quantum fluctuations push the field downwards, inflation will stop. But this is exactly the problem. So what we have is a picture where in some regions, the inflaton is kicked up in the potential field, and then inflation continues. So we have a patch that is continuously expanding, whereas some other areas around inflation stops. But this can happen at any point in space, at any point in time. And the resulting picture is that I'm just going to have randomly distributed patches of space-time that are just inflating in time. And whether inflation ends there or it does not end, it's also a separate question. But what will happen is that, for instance, if this field inflated and then, as you say, then the quantum fluctuations kind of stop the inflation or whatever, at least stop the decline of the field, then inflation might stop and we might end up in one of these patches in our observable universe. But the consequences of this is that we're going to have different regions on the broader spectrum of our space that are kind of disconnected universes in which inflation happens at different times and at different times. We end up with different values of the densities in these regions, which then affects large structure formations, etc., etc. So what happened is that we end up with a picture of an inhomogeneous universe on the larger scale, but we are somehow here, and there's no way for us to know or reach what's here. And these bubbles of these inflating universes are running away at each other at the speed of light, because this boundary is expanding at the speed of light. So these boundaries never touch, but they keep inflating inside and running away from each other. So instead of having a theory that predicts for me, why did I end up in this patch of the universe, or for instance, why does my universe look like this from where I stand, I end up with a theory that tells me any type of inflation could happen at some point in space and time, and therefore our location, our observable universe is not really unique, but it's just a random statistical possibility from all of these possible other universes, and this might have consequences on the constants of physics that are used there, and we hope that the physics that we come up with and the theories we build are universal and fundamental, but this is not the case. What happens, it just happens that we end up in just a random patch. So this exactly is the point that challenges the paradigm of inflation, because you start from a point where you want to explain the observables, you end up with, instead of explaining why you have these observables, you end up with a picture of anything that could happen will happen, and it's just by random or random possibility that you ended up in this patch. And this is a very lousy explanation, and this is not a footstone to do and to make any predictions about our universe on any scale. And if we then maybe started from a different patch of the universe, our conclusions on what could be around might have been different. So this is exactly the challenge to this predictability in the theory of inflation. So this is why self-reproduction and the appearance of these multiverse, this multiverse picture is problematic. I hope I convinced you of this for now.
One more question.
Yes.
In slide, previous slide.
Yeah.
So you said if you start inflation at Planck scale, so in what sense? I mean, the Planck
So Planck scale, the Planck curvature scale. So that the Hubble constant is 1 in Planck units, for instance.
So you mean Hubble scale is Planck scale?
Yes, the curvature scale is the Planck scale.
And
Okay. Yes.
This is my question. By the way, I don't know whether I well understand or not, but if we the human,
If we what?
if we are started in the other patch,
Yes.
then we mean our fundamental theory can be different. This is your meaning? Or?
Yes, because I mean, depends on the residues of the scalar fields. It's going to affect then in the reheating phase, if hopefully that happens, the concentrations of different particles in our universe. This is going to affect the way we analyze them, the way we hypothesize things related to them. So in some sense, it will affect our fundamental theories that this picture kind of puts on shaky ground. And maybe one more point, last point about this is that this puts us actually back to square one, because in principle, inflation was proposed as a solution to the problem that our universe did not randomly constitute of these infinite patches of causally disconnected regions that are somehow homogeneous, flat, and equilibrated among each other. Because then what difference does it make to say, oh, our universe is the way it is because it happened that at some moment in time, all of these patches became equilibrated, and then the observable universe became homogeneous or whatever. It's the same footing, it's the same chance as for us to be in just any patch, any inflating patch of the universe, and then observing what we observe today. So this kind of undoes this explanatory gap of why our universe is the way it is. And tangentially, while we try to solve that problem, we are also challenged with the idea of what could be also the simplest problem that can solve for us the flatness problem, homogeneity problem, the multiverse problem, and for it not to be overcomplicated with many parameters. But this is not really a solid argument in the sense of it has any basis other than what we understand historically as a nice theory that explains reality. This kind of stems from our understanding from about the naturalness of a model, of a theory, that we always tend to just prefer models that are kind of simpler to explain. However, since Planck favored plateau models and ruled out completely, for instance, power law inflation models, plateau models are definitely slightly more complicated than power law inflation because of it needs much more parameters to tweak to get it. So the observation is really telling us that, okay, we do not need to go that simple to try to, for the model to be comparable or replicate for us the observations that we have. So we really should not really seek the simplest, but then just try to be as simple as possible to explain what we have, but not really criticize everywhere that there is some modification, some change. Because, for instance, in this model, it's quite simple. This is Shabashnikov's model, which uses the Higgs boson as the inflaton. And they actually achieved inflation by strong coupling, by non-minimal coupling of the inflaton field to the curvature. And this model is not ruled out by Planck. In fact, it is one of them. It's also a plateau model. If you go from this frame to the Einstein frame, you'll get a potential that is a plateau potential. So it's one of the favored models. You could argue that this is indeed a simple model, but also we have Starobinsky inflation. Starobinsky inflation also has not been ruled out by Planck, and it is also one of the models that are somewhat favored, because also if you go to the to another frame where and okay, of course, Starobinsky model is a modified gravity model, which adds a square term of the scalar curvature into the action. But then, of course, any function of this form of the scalar curvature can be transformed. The action can be transformed, and then we can get into a picture where this f of r is just explained by also a strongly coupled scalar field to not strongly coupled, non-minimally coupled scalar field to gravity. Okay, so this gravity modification is also a model that is favored by Planck. It is not ruled out, and in fact, once you do this transformation, the effective potential that results is very similar to the one which to the one of the Higgs inflation I showed a bit before. But this is quite exciting, because here we are stepping a bit, we're taking one further step to say, okay, I'm not gonna reduce my potentials to the simplest possible, but also I'm gonna allow gravity to be modified to explain these observables and hopefully answer as many questions as I can without being limited to classical gravity, the way it is the general relativity is formulated, but also allow some room for modification, which is going to be the stepping stone of the framework in which we build our theory, which subscribes to models of to theories of modified gravity. Okay. So in general relativity, modifications of general relativity are needed. We all know that. We need them at Planck lengths. We need them to solve problems related to singularities, cosmological singularities, black hole singularities. So there are a lot of motivations for people to diverge towards modifying general relativity. Normally, however, modifications of gravity involve adding new fields. For instance, on the slide that I showed before of Starobinsky model, it started as a curvature modification of the action, but then this picture is equivalent to the picture of a scalar field non-minimally coupled to the curvature. So in fact, we added a scalar field degree of freedom to the theory. But in mimetic gravity, which I'm going to introduce next, it is a modification of general relativity. However, the degree of freedom of the field that we introduced is not going to be dynamical. Therefore, with a disclaimer, if I want to say, we are not adding a dynamical degree of freedom to the field like other models of modified gravity. But a gravitational degree of freedom will get excited, which is why it is kind of called mimetic. It's a mimetic field. So we introduce a field. It will turn out that it is not dynamical, but a degree of freedom of gravity will play this role of the modification. And hopefully I'll be able to explain it in the next slide. So, mimetic gravity was actually introduced by Slava and Ali Shamsuddin in 2013. It was formulated a bit differently from this action. It was formulated as a scale transformation on the metric. And we know that scale transformations usually do not leave GR invariant. But in this case, we wanted to leave GR invariant. So you have to put some constraint on this field. And this is quite obvious because we said we don't want the scalar degree of freedom to be dynamical, so we have to constrain it. So I did not show the previous formulation of this model, but in its new form, you just add to the action of gravity a constraint on this mimetic field or scalar field that you're adding, in addition to whatever Lagrangians or matter you want to add. So this constraint on this field is important because this is what will prevent the degree from being dynamical. So it's like a mimetic, it mimics a field, but it modifies gravity within the degrees of freedom that gravity has. So if we want to be accurate, so we have 10 components of the metric, we added a scalar field, we subtract from it the constraints, and then again we are left with 10 components. This is just no degree of freedom for the scalar field is added.
Right. But could you go back to the slide? Oh, okay. We can always redefine the scalar field by here.
Here?
Yeah.
Redefine it.
So lambda is just a question of kinetic term, right?
Lambda?
Yeah, lambda.
Lambda is actually it's a Lagrange multiplier that allows me to put a constraint in the action, and you will
Okay,
see
so
later
It's field.
it's what?
Lambda is a field, not just a constant.
Now you will see that it's not actually a field. So if you just wait one more slide, I will maybe hopefully convince you that it's not a field.
Okay, because if lambda is just a constant,
Yeah.
so we can always redefine the scalar field
Well,
to answer the question.
perhaps you will be able to redefine it, but maybe when I just go one slide further, it will be clarified what this field really is, and then your question will clear out a bit. Because I agree with you, I am saying that, oh, I added this scalar field that does not play the role of a scalar field then. What is this field? Well, if I solve this constraint that I added to the action, what I get is that the solution for the scalar field represents just the time coordinate with a shift invariance. So what this gives me is a natural way to slice space-time into three-dimensional hypersurfaces in space-time. I just took this equation, I solved it, this is what I got. So my scalar field is really just a time coordinate in the synchronous gauge, which allows me to slice space-time into hypersurfaces, which is why maybe now you can say that I can redefine it. Yes, you can. In fact, that in different gauges, it will have a slightly different definition, but it will have the same meaning as this coordinate transformation thing. And to go back to the lambda part, so what we do is we do the standard, we take our action, we derive our field equations that now have a modified part that comes from the contribution of this mimetic field, and an energy momentum tensor that comes from the contribution of the matter Lagrangian that you choose to put in your action. If there is no matter Lagrangian, if there is no matter at all, in fact, you are still going to get some effect, which is right here. So if we vary the action with respect to this field phi, and we solve this equation, what we get is a solution for the lambda, which is going to be an integration constant over the determinant of the three-dimensional metric, because we use the synchronous gauge. So and for example, in a flat Friedman universe, if I just use the metric of a Friedman universe, this lambda is going to be a constant over a cubed, the scale factor cubed, which is what we know as the dust component or the dark matter component. What this is telling me is that if I don't include matter at all into my Lagrangian and only the constraint, I'm going to end up with a degree of freedom which mimics dark matter component, hence the name mimetic dark matter. So this was the original idea of this field, and it was because there were different, and even today, different directions are still conflicting between whether to account for dark matter as a modification somehow of gravity, or there's an endless search for the next particle that's going to be So this subscribes under the geometric interpretation of this dark matter, the missing dark matter in our universe, just from this very simple modification into the action. But as I said earlier, we try to have a very simple model and at the same time answer as many questions as possible. So what was realized later is that this action with the constraint, with the mimetic field introduced, you can expand it a bit as to introduce an invariant that depends on the scalar field, which is nothing but the Lambertian, which is the contracted second order covariant derivative of this field. And it turns out that this also has a very simple physical meaning. And on these these hyper surface slices that we define, it's going to be nothing else but the extrinsic curvature on these hyper slices. And by adding functions of this term into the Lagrangian or into the action, we will be able to solve much more problems. So in some sense, it is like adding some curvature to the action, but through this mimetic field. And of course, the extrinsic curvature is defined with this equation just normally. And I will just provide a couple of examples where this has been used before. So by putting this constraint and the simple function of this box phi, previous works of Slava and his collaborators were able to find solutions of non-singular black holes and resolve also cosmological singularities. But for this talk, we're going to go back to the self-reproduction and multiverse picture, and we're going to use this function of this scalar invariant to hopefully solve the problem of self-reproduction and end up with the least degree of fine-tuning. So this is finally the Lagrangian of our theory, the action of our theory. The constraint, the inflaton field, which this is the normal kinetic term, but here we couple the potential to a function of this kappa or box phi. And in principle, at the level of the action, you should add box phi here, and only later when you define the gauge, you can then just define it to be k, kappa. So consider this a typo. And in fact, this coupling function is very, very simple. It will give me modified Einstein equations with a modified energy momentum tensor. Looks a bit complicated, but in fact, it's going to be very, very simple. And the modification to the background equations that we have seen before in the Plateau models is going to be very minimally modified. So for a generic coupling function, what we have is, again, we can solve to obtain lambda, and it will give us this dust degree of freedom and a small contribution, because now we have extra components in the action. And so the change in the Friedman equation will just be this factor that is standing before the potential. And in the equation of motion for the inflaton, we're also just going to have this factor, this function, coupling function, standing next to the potential. At this level, this is all the modification that happened. So now, to illustrate our idea, we just choose a very typical plateau potential. It can be different, it can be anything, but this is the one we chose to demonstrate the idea. And here I want you to see that the coupling term is indeed very simple. So it's just one, which is just like adding the potential itself. And the coupling term is just a linear function in this extrinsic curvature. And m is the mass of the inflaton field. So in fact, this modification is only applied at high curvatures, because when the extrinsic curvature is very, very small compared to this mass, what we obtain is the old picture of just the plateau model of the inflaton field. So this modification is we only add it at high curvatures. And in this potential, just to make it a bit clear, we divide the potential where phi is less than 1. Here is usually the region where reheating happens, etc. So we will not be considering that area. because we want to see how inflation starts and how we stop self-reproduction. So we will be considering this part of the potential. And in this part of the potential, we just take a slight limit of this potential, not to use the whole thing, but this is just a detail.
Sorry.
Yes.
I'm a bit confused about
Yeah.
dimension of potential.
Okay.
So phi is just scalar field.
Yes.
So dimension 1. I mean, I'm just asking the phi is the bigger word.
Maybe I
in
should.
Which,
Maybe I should make it a bit clearer than at which point here. Yes, so here you can see a cursive phi, which is the inflaton, and this phi, which is the mimetic field.
okay.
Just not to confuse you later. So this is the kinetic term of the regular inflaton field, and here it is. But this phi, it's an unfortunate choice of Greek letters.
And I understand, but
Yeah, okay.
then what is the dimension of m in your later example?
Well, actually, here we work in Planck units, all in Planck units. So even m is also in Planck units.
Then little bit strange that the dimension of v. Show me again. Yeah. So v should be dimension 4, right?
And everything is measured by Planck unit.
In Planck unit.
Yes.
Then
So m and phi was dimensionless.
Yes.
I see. So here then the meaning phi less than 1 or bigger than 1 means it's larger in Planck unit. So
Yeah, it's just
Bigger
the
than
field
Planck or-
value.
bigger than Planck or smaller than Planck. I see.
Okay.
Sorry, could you again explain the relation between kappa and unique field?
Yes, of course.
So kappa is a function of the unique field.
So kappa is not a function in regular general relativity. Kappa is just defined as the extrinsic curvature on the hypersurfaces if I define a certain slicing. It happens here that if I compute the Lambertian of my mimetic field, it will have this definition, which coincides with the definition of the extrinsic curvature, which is why it is apparently equivalent, because this was not realized before, but it was realized after, which then allowed us to manipulate the action using functions of this sort of terms. So they have the same definitions, therefore.
So in the case of Friedman universe,
Yes.
kappa is a function of A.
Well, if we usually use the metric of a spatially flat Friedman universe, but yes, actually the kappa will be a function of
So you just double quotes.
yes,
Scale function.
yes. Okay, so we go back to the relevant part of the potential for the field, and here again we have two parts that are at play for inflation. So as I said before, in the plateau models, what usually contributes most to the inflation is the potential part, right? Because the field is slowly rolling, the kinetic energy is much less than the potential. But here, in fact, in this region of the potential, we have inflation that is dominated by the potential, but larger than these scales of M, we have inflation dominated by the kinetic term. So our second time derivative for the field in the inflaton equation of motion is still very negligible, comparable to the other terms. However, in our case, this does not imply that inflation is strictly driven by the potential. It's in the other part of the on phi greater than these values, it is actually driven by the kinetic term, which is going to be the key moment where we avoid the self-reproduction. But for now, let's analyze this part of the potential, and let's see if the conditions for self-reproduction is satisfied here. So the potential is dominant. The Hubble Friedman equation h squared is mostly proportional to v. I then calculate the decline of the classical field with this equation that I derived earlier. Here I plug in the value for phi from the equation of motion, phi dot, and h is radical v. And then the quantum contribution to this mean value of the field is again, the amplitude of that is again proportional to h. And as it happens, it is always less than 0. So the condition for self-reproduction is always violated for this part of the potential where inflation is dominated by the potential. So let's see in the other part. Now in this part of the potential, where, by the way, the curvature is also very high, so this is kind of the reason why phi dot becomes dominant is because of this modified contribution of this kappa. So now h squared is proportional up to a numerical factor to my kinetic term. And again, I compute the decline in the classical field, where here now h is approximately phi as well, so it is of order 1. And the decline in, the contribution of the amplitude of the quantum fluctuation is also of order h. So the total value is going to be h minus 1. So this is also a key moment in our model, because previously in the plateau models, we saw that if we wanted to start inflation at the Planckian curvature scales, what happened is that the slow roll condition prevented the field from decreasing enough, and it was counteracted by the quantum perturbations. So in slow roll there, we could not start inflation from a Planckian scale of curvature and not end up with self-reproduction. Whereas here, if we start h at Planckian values or sub-Planckian values, we are guaranteed that the total change in this mean field value is going to be decreasing, and therefore this violates the condition for self-reproduction, and we will not have self-reproduction. So one important point here is that we do set a constraint, therefore we say that we should start inflation at Planckian scales of curvature, but to some degree it's a lesser form of fine-tuning than, say, trying to make all of these positive disconnected regions have certain initial conditions to then start inflation without self-reproduction. This problem of self-reproduction and high level of fine-tuning are not reconciled in typical plateau model inflationary scenarios. However, here, if we accept the lesser level of fine-tuning and say that inflation should start at Planckian curvatures, we successfully avoid self-reproduction. Is this clear? Because this is the key point of this one. So now I move to the last part of my talk, which is the cosmological perturbations. It happens that our little modification in the general relativity action does not lead to any changes in the gravitational wave spectrum, but we will see there are a lot of changes that are happening at the scalar perturbation level. We, of course, perturb the metric in the Newtonian gauge, and once we perturb the constraint equation, we get that the first-time derivative of the perturbation in the mimetic, this field, is equal to the scalar gravitational potential from the of the perturbation of the metric. So this also says that we don't have a separate mimetic field that has a certain spectrum, which is consistent again with our picture that this phi is just time component in this whole picture, and it merges into other variables that were already there in GR. And it happens that the only relevant equations from the perturbed Einstein's equations are going to be 0, 1 equation, which is this one here. This is the only extra part that we have. And I feel like I'm missing a term. Okay. And the perturbed equation for the inflaton is this very big equation, but it will be reduced a lot when we take the case for the short scale perturbations and the short wavelength perturbations and long wavelength perturbations. So we're going to consider plane wave perturbations, and first we're going to look at the short wavelength perturbations, where the gravitational field perturbation is oscillating, and if we inspect the linearized equation of motion of the perturbation of the inflaton, we can see that this term here, in comparison to this term here, is suppressed by this factor, which in inflation is very, very small, h dot over k over h squared. And these two terms, in comparison to other terms in this expression, are also suppressed by a factor which is much, much smaller than 1. So effectively, we end up with a very simple equation that gives us exactly just the Minkowski vacuum spectrum of perturbations. So here, there is nothing magical happening. At the considering long wavelength perturbations, this term will be dropped out because it's a spatial derivative term, and also in the 0i equation, also this term drops out. We are left with these two equations, which surprisingly give us, we are able to find exact solutions for these equations, which in their general form are the same solutions we already obtained in general relativity. But the specificities of these solutions are going to depend on details from our evolution picture of inflation, which is of course different than the other cases considered. So now here, before we want to compute the spectrum of inhomogeneities, we want to find the amplitude, the constant, and the way we do that is the very usual way. So this term here, we can expand, and during inflation, we can drop out this decaying mode, and this h dot over h squared is also very suppressed. And the relevant part for us is that we know that once the perturbations are crossing the horizon, their wavelength is proportional to inverse Hubble scale, and therefore the amplitude is proportional to h. So using this information, at the moment of horizon crossing, we can fix A to be this, just by putting delta phi equal to h and shuffling around. So A will be evaluated at the moment of horizon crossing. And then we put it back into the gravitational scalar perturbation. And we finally obtain the spectrum of the gravitational perturbation and the gravitational waves. So as I said, the gravitational waves spectrum remains the same as in GR, and it is proportional to h. And here it is h squared over the derivative of the field evaluated at k equal ha. But here, as you can suspect already, because at some point my modification into this whole picture resulted in a small interval where h squared for me is proportional to the velocity term, not to the potential. So here is exactly where I expect for a small change to happen for the scalar perturbations. And of course, relevant to observations, in the region of observations, the spectrum index that is obtained for example, n equal to 50 is in agreement with observations, and the tensor to scalar ratio is still within the upper bound of what we know for the R to be. And on the side, if we compare our scalar tensor to scalar ratio with, for instance, Higgs inflation or Sarabinsky inflation, I think they have 1 over n squared. But if we slightly maybe, because again, all of this is specific to the potential that I chose to illustrate the example, but then maybe if we change somehow the potential, you can also make this a bit smaller, but this is still within the acceptable region. And finally, I'm just going to show a...
In the usual inflation case, the denominator phi naught is related to the epsilon, right? To reply.
Sorry, here?
Yeah, yeah.
Yes? It's related to what?
It's related to epsilon, the one with the slow roll parameters, right?
Okay.
So in this case, in your case, so is it also the same? Or-
So if you noticed, I tried to go through this whole talk without mentioning the typical slow roll parameters because our equations are slightly modified. Therefore, it is not possible to define the same slow roll parameters in our equations as they are in other Plateau models. So I wouldn't say any statement about that.
Okay.
But
So
what?
then-
Yeah.
So then you don't have any analytical expression for that.
For this?
Yeah, for that. Yes.
I mean, we could only solve it with for each part of the potential separately, depending where, for instance, potential dominates, kinetic term dominates. But the graph of these is actually obtained numerically, so this is an exact solution. But it coincides with our analysis. So in the paper, we analyze each part separately, and we write the way this increases, decreases, and the limits coincide with a numerical analysis. So I would say we are super safe. And the exact analytic expression is only within the different limits where we can apply our approximations. So what happens, so again, so these are the amplitude of the spectrum for the scalar perturbations. It's this one here. So here the colors do not help me, but the black one is the one for the scalar perturbations, and this gray one is for the tensor perturbations. And as we see in the beginning, it's increasing, I think, as a function of phi cubed, but then it starts decreasing again, and it rejoins with the tensor perturbations. And I would like to notice that this part where it rejoins with the tensor perturbations is exactly the part where the kinetic term dominates over the potential, which then makes h squared proportional to phi squared. So then h squared over phi, h squared over phi is nothing but h, which is the same as the tensor perturbations. So this is one major difference that we obtain. And also it is worth noting that up to the Planck curvature scale, for which phi is this value m to the minus 2 over 3, if I choose to describe phi in these units, all of my perturbations are less than 1, which is also consistent that I do not have any self-reproduction. If I start inflation from here onwards, and the part that is relevant to the observations, it is within the range of 50 to 60, E folds is somewhere here, and it is consistent with the observations. So, just to conclude and make sure I got my idea, brought the idea home, in the known models, it was not possible to reconcile fine-tuning and solve the problem of self-reproduction reasonably in one model. So you either have to give up one over the other, and both lead to, let's agree, to tragic conclusions. One touches on the predictability, and one leads you back to the problem of extreme fine-tuning of initial conditions. However, in our model, which is, I remind you, a modification at high curvatures without adding extra scalar field degrees of freedom, we were able to obtain, we were able to avoid self-reproduction and hence the multiverse with the condition that if we start inflation at the Planck curvature scales, and it's basically depends on the types of potential that you include in these models and maybe different coupling functions. You can then find different models. However, I would like to stress that our coupling term, which was just 1 plus k technically, it is the simplest, but it is the most crucial because this k coupling is the one that allowed the kinetic term to play a role in inflation at the beginning and prevent slower self-reproduction from happening at the beginning. So we have not yet explored other coupling terms that solve the problem other than the one that we have presented in this paper so far. But the choice of the potentials and all the other details could be tweaked around, etc., etc. So, and maybe one last word about the trans-Planckian problem, that we do not consider this a problem because the relevant quantum perturbations that then are the ones that exit the horizon during inflation and then evolve there and then come back. But the idea of trans-Planckian problem is that so if inflation is happening over a long period of time and you're starting with the smallest possible quantum fluctuations, these fluctuations are expanding space, exiting the horizon, whatever is happening to them there. But at some point, the quantum fluctuations that are outside of the horizons happen if we consider the time scale at which these events happened. If you trace it back, it appears as if these quantum fluctuations originated from length scales that are smaller than Planck scales. However, this need not be the case because we have the uncertainty principle and it is responsible for creating in the sub-horizon scale these perturbations with the appropriate amplitudes and wavelengths. So you do not need to say that, oh, I borrowed from the sub-Planckian length some perturbation and evolved it outside of my horizon. But the way the equations describe this process, it's because it's smooth transition. Our equations describe smoothly the evolution and expansion of these modes outside of the horizon. But this is simply just to aid us help us to trace these amplitudes and these quantum fluctuations, because then the alternative would be to start at every scale and put an initial condition at every scale and every time trace this one mode that you created with this uncertainty principle and trace it. So the equations kind of hint that these modes that are present today came from Planck lengths, but that's not the case. They were generated inside the horizon at some moment in time because quantum fluctuations are appearing at every instant. They are continuously generated, so we do not need to assume that they came from some sub-Planckian length. But unfortunately, and this is a peculiar thing in our field, is that some discussions never seem to end because there is no one to say that, oh, this problem is solved, let's move on. And a lot of papers are still being written about this problem, discussing this from different angle, completely ignoring this very simple fact, but we have to deal with this. We have to keep addressing all of the criticisms continuously. So I hope I was able to address most of the criticisms that are somewhat reasonable in our framework, and thank you for listening.
Thank you very much for the nice talk. Any questions?
I'm a little confused here. For example, I use the slow inflation.
Yes.
And I assume the kinetic energy is dominated at the beginning.
Okay.
And
Sorry, you use or we use?
not your field. I imagine the
Yes.
slow inflation.
Yes.
Chaotic.
Okay.
And assume in the beginning the kinetic energy dominates over the kinetic.
Yeah. So
Then I don't have this.
no, but in usual plateau models of inflation, if you have a similar potential to this, then if you are somewhere here, then of course you are starting with enormous kinetic energy. But what happens is that inflation does not start until the field hits this plateau.
Yes.
So the role of the kinetic energy there is to just drive the field to the attractor, to this plateau, and then inflation will start.
Yeah.
So we consider our analysis for the self-reproduction condition, for example, the moment inflation starts. But in our case, inflation is even driven by the kinetic energy in this
It's
here.
inflating.
It is inflating during the kinetic, yes.
Okay.
Thank you for the question, the clarification.
Maybe related question. So I thought, yeah, same thing, but why we need that plateau region? Then we just can occur the inflation during if the kinetic energy can dominate and also drive the inflation, then we don't need the plateau.
So maybe you should
potential.
join us on working on the new model that we're developing. It's an interesting question. We have explored different sizes of the plateaus, but in this current, for instance, at least with this coupling term that we have used, it was not possible to generate today's observables without adding this plateau. But this also supports our idea that our modification is really only happening somewhere here at high curvatures, whereas here you are kind of, and even in this region around here, this coupling terms become slightly negligible with one. So here, so in this region, technically, inflation proceeds like normally. So our modification is applicable at the onset of inflation to prevent self-reproduction from happening at the beginning. And then you kind of proceed the regular way, because otherwise you will need to account for what other signatures your modification at these scales is. And we have not explored that yet, but that's an interesting thing to explore.
Another question is, in this model, when do you think that n equals, for example, 6t? So it start from there, or I mean, when is the field value?
Yeah. It doesn't have to start from the field value. I labeled it on here.
I mean, I'm concerning that the observational constraint kind of how to say.
So if you start, so our constraint is really to start inflation below this point, like starting from the Planck curvature at this point and below. But if you want to start inflation here, that's not a problem as long as you are kind of in the sub-Planckian curvature scale.
But in that case, we cannot distinguish your model to our model. Right?
You can, because up until only somewhere here where this coupling term becomes irrelevant, but throughout most of this region, this coupling term changes slightly the structure of the equations, and then you are left with the picture that we see. Because you can even, I think, show it here. So notice this equation, okay? This is the equation of motion. This is our coupling term. When I ignore the second time derivative here, and I want to get an expression for the first time derivative to plug it in my change of the classical field value, right? Normally, what happens is that I don't have this here. And what I have is the derivative of the potential divided by k, right? Which is the Hubble constant. But here, this and the potential are multiplied by the k, so it drops out when you plug it in here. This is an order of radical v less than than in the regular plateau models. So you do see a difference even here.
For example, using which observation? For example, power spectrum, or not power spectrum, but for example, the non-Gaussian T really affect.
I mean, at this stage, we're only concerned with the condition whether self-reproduction is the condition whether it's violated or not, because we are just checking here if we start indeed inflation here, or here. We do not satisfy the condition for self-reproduction, and we do not enter the regime of eternal inflation. The part that concerns the observations is the perturbations part, and in the region of observations, the relevant part of the observations, it fits. And even if in that part, maybe the K does not play a major role, but it's already, so anyway, it's not like if I have a plateau model with self-reproduction, multiverse, I cannot observe these universes and I will never be able to do that. But then we can trace with equations what we expect to happen. So even this self-reproduction multiverse problem is not, it's not a problem that exact observations are concerned with, but there are consistency problems with our theory that we are concerned with. So yes, maybe in the observable part, the modification will not play a major role, but in the whole scenario and these problems that test the ground on which the inflationary theory is standing, this is important.
Is there any characteristic observational prediction of your model?
Other than the
Power spectral assembly, is there any other?
not that we have thought of yet, but just like other models, we look for the parameters that you can extract from observations. But yeah, it would be interesting to kind of try to differentiate these and others with some other different signature, right?
Yeah, because you are trying to explain that your model in theoretical point of view is better than other models.
Yeah, so we solve. Yeah, we say that. Oh, we solve also cosmological dark matter. Oh, we solve this, that. But yeah, as you say, it's not yet. There's no definitive.
Theoretical, but we in the final part we need to distinguish all of these models by the operation.
We welcome you to think with us on that.
And what about the tensor perturbations? I mean, could you show me once again about?
It happened that once we did the perturbations, the equations were identical to the ones that are already in GR. So we did not obtain any differences for the spectrum of the.
That's actually what I'm the part of what I'm. Could you show me the next slide?
Mm-hmm.
So what is the part that linearly flowing? Maybe I'm confused. Maybe I mean.
So here the
inflation is so that the horizontal line is for the modes come out to the.
So this is basically as a function of phi, basically at which the field was at what stage the field was at when the perturbation left the horizon. So that this the part where the kinetic term plays any role to change the kind of the scalar or even the wave tensor perturbations, as you say, because then h is equal to phi dot. It's here, but this is outside of our observational
so that's
region.
It's when is the observational reason? I mean, current.
It's somewhere here.
I see.
Yeah. And phi dot really plays a role here at the onset of inflation, if you choose to start inflation.
If not, let's thank Speaker again. Thank you very much.